Welcome to G Fun Facts Online. Today, we are going to dismantle a very common misconception about our universe. We often view the cosmos as a silent, static void, a place punctuated only by the steady, boring orbits of dead rock and ice. When we think of comets, we think of dirty snowballs tumbling passively through the dark, waiting for the sun to melt them a little bit. But in the cold reaches of our solar system, and indeed coming from the interstellar void beyond, there is a class of celestial bodies that defies this stillness. They are geologically dynamic, they are explosive, and they are thermally complex. These are the cryovolcanic comets. These are active ice worlds that blur the line between inert asteroids and living planets. With the recent groundbreaking observations of the interstellar object 3I Atlas in late 2025, and the persistent, violent outbursts of the space volcano known as 29P Schwassmann-Wachmann, the scientific community has been forced to rewrite the book on cometary physics. We now know that these bodies are powered by exotic thermophysical engines. These are mechanisms of heat, pressure, and phase transitions that can tear a comet apart from the inside out. In this episode, we are delving deep into the heart of cometary cryovolcanism, dissecting the thermal physics that turns frozen drifters into erupting geysers of gas, dust, and, as we have recently discovered, exotic metallic vapors. Let us begin by defining what we are actually talking about, because there is a critical distinction between a normal comet and a cryovolcanic one. Traditionally, cometary activity was described as simple sublimation. That is when sunlight warms the surface ice, turning it directly into gas, or outgassing. This gas drags dust along with it to form the beautiful tail we see from Earth. This is a passive, surface-level process. Cryovolcanism is fundamentally different. It is an endogenic or internal process. It requires three specific conditions. First, you need internal pressure buildup. Gas must accumulate beneath a sealed or semi-permeable crust. Second, you need structural failure. The pressure must exceed the tensile strength of the material holding it back. And third, you need an explosive release. This is a violent ejection of material, called cryomagma, which in the vacuum of space consists of gas, ice crystals, and dust. While a terrestrial volcano here on Earth erupts molten silicate rock driven by buoyancy and dissolved gas, a cometary cryovolcano erupts volatiles. We're talking about water, carbon monoxide, carbon dioxide, and nitrogen. These eruptions are driven by the thermodynamics of phase changes in a vacuum. But this begs the question, comets are small. They are usually just kilometers in scale. They are cold. They lack the radioactive core heat of a planet like Mars or Earth. So where does the energy for a violent explosion come from? The answer lies in a fascinating combination of solar insolation, chemical potential energy, and phase transition physics. The most potent energy source hidden within a comet is something called amorphous water ice. This is formed in the frigid, pre-solar nebula at temperatures below 100 Kelvin. In this state, water molecules are randomly arranged, like glass, rather than ordered in a crystal lattice. This amorphous ice acts like a battery. When it is heated, even slightly, it undergoes an irreversible phase transition to crystalline water ice. This transition is exothermic, meaning it releases heat. This creates a chain reaction. As a heat wave from the sun penetrates the comet's crust, it triggers this crystallization. The heat released by the transition warms the adjacent ice, triggering even more crystallization. This creates a self-sustaining crystallization front that propagates inward, deeper into the comet. Crucially, amorphous ice has a sponge-like ability to trap hypervolatiles, like carbon monoxide and nitrogen, within its disordered matrix. When it crystallizes, the lattice tightens, and it expels these trapped gases instantly. This sudden release of trapped gas creates a massive spike in localized pressure deep underground. If the crust above is sealed, the comet becomes a pressure cooker. When the pressure breaks the surface limit, the crust blows open. But not all outbursts require this exotic transition. Simple sublimation can turn explosive if the geometry is right. Imagine a subsurface cavity filled with volatile carbon dioxide ice, covered by a layer of non-volatile dust or water ice that has been sintered or fused together by solar heating. This creates a sealed pocket. The dark, dusty surface of a comet absorbs sunlight efficiently because it has a low albedo. This heat conducts downward. If the volatile ice inside the pocket sublimates into gas faster than it can diffuse through the pores of the crust, pressure builds. Cometary material is incredibly weak. It is often described by geologists as having the consistency of dried cigar ash or meringue. It takes very little pressure, just a few kilopascals, to shatter the crust, resulting in a collimated jet of debris. Now, let us look at the chemical complexity, the ingredients of such an outburst. The lava of a comet is a frigid slurry of gas and solids. We have the standard volatiles like water, carbon monoxide, and carbon dioxide. Water drives activity near the Sun within 3 astronomical units, while the carbon compounds drive activity in the distant solar system out to Neptune's orbit. Then we have the supervolatiles like nitrogen, oxygen, and argon. These are found in pristine comets from the Oort cloud. They sublimate at incredibly low temperatures, around 40 to 50 Kelvin, allowing comets to erupt even when they are as far away as Pluto. But the new frontier is organometallics. The 2025 analysis of the interstellar object 3I Atlas shocked the world by detecting nickel tetracarbonyl. This is a volatile compound that creates a form of metallic cryovolcanism. It sublimates at low temperatures, carrying heavy metal atoms into the coma. This suggests that in some alien solar systems, comets are not just icy dirt balls, but chemical factories processing complex ores. To truly understand the physics, we must look at the case studies, the monsters of the Midway. First, consider 29P Schwassmann-Wachmann. Orbiting between Jupiter and Saturn, 29P is a centaur, a refugee from the Kuiper Belt transitioning into the inner solar system. It is the most volcanically active body of its size class. It does not have a tail in the traditional sense. Instead, it brightens by factors of 100 to 1000 in mere hours. 29P is likely in a state of runaway crystallization. Its large nucleus, roughly 60 kilometers across, retains enough internal heat to keep the amorphous to crystalline front moving. The 57-day periodicity of its outbursts suggests a link to its slow rotation, where the day side bakes long enough to trigger deep thermal pulses. The super outbursts observed in the mid-2020s have ejected millions of tons of mass, suggesting large-scale crustal collapse into evacuated magma chambers below. Then there is 12P Pons-Brooks, the so-called Devil Comet. Returning to the inner solar system every 71 years, 12P made headlines in 2024 for its horned coma. The mechanism here was fascinating. The horns were actually the shadows of a massive block of crust, blocking the outflow of a specific cryovolcanic vent. Unlike 29P, 12P dives close to the Sun. Its outbursts are driven by intense solar heating, creating pressure bombs, where pockets of liquid hydrocarbons and waxes, or superheated subsurface ices, vaporize instantly upon crustal failure. We also cannot forget 67P Churyumov-Gerasimenko, the Rosetta standard. The Rosetta mission gave us the most detailed look at cryovolcanism at the microscale. It observed deep circular pits in the Seth and Mott regions that were not impact craters but collapse features. These are sinkholes formed when subsurface volatiles vent away, leaving a void. We witnessed the Aswan cliff collapse, a landslide triggered by thermal stress. The exposure of fresh, bright ice to sunlight caused an immediate, localized outburst. It was a dry landslide triggering a wet eruption. And finally, the anomaly, 3I Atlas. The detection of this object in 2025 introduced the variable of exotic compositional thermodynamics. Spectroscopic analysis revealed a coma rich in atomic nickel and carbon monoxide, with a distinct lack of water compared to solar comets. The theory is that this object likely formed in a carbon-rich, oxygen-poor protoplanetary disk. Its cryovolcanism is driven by the sublimation of nickel tetracarbonyl, a highly volatile liquid or gas that forms from the reaction of carbon monoxide with nickel grains. This toxic volcanism operates at different pressure and temperature regimes than water ice, allowing for sustained jets even at large heliocentric distances. So how does a cryovolcanic vent die? The thermophysics dictates a cycle of activation, erosion, and dormancy. First, activation occurs when thermal waves reach a pocket of volatile ice or amorphous ice, and pressure builds. Second is the eruption, where the crust fails. Gas expands supersonically into the vacuum, accelerating dust grains to hundreds of meters per second. Third is collimation, where the walls of the vent act like a rocket nozzle, focusing the jet. Fourth is erosion. The jet scours the walls of the vent, widening it. Eventually, the nozzle becomes too wide to maintain pressure. Finally, quenching. As the volatile fuel is exhausted, or the vent widens enough that sublimation cools the remaining ice through evaporative cooling, the eruption ceases. The vent fills with fallback dust, becoming a smooth terrain trap, waiting for the next thermal trigger. Why does this matter? Understanding the thermophysics of these active worlds is about more than just curious explosions. It touches on planetary formation. The energy released by amorphous ice crystallization might have been enough to melt water on larger Kuiper Belt objects like Pluto or Charon early in history, potentially allowing for ancient subsurface oceans. It touches on the origin of life. Cryovolcanism is a delivery mechanism. It dredges up material from the deep, protected interior of a comet, where complex organics, amino acids, and prebiotic molecules are shielded from radiation and sprays them into space. If a comet strikes a planet, it is this cryovolcanic payload that seeds the surface. And it matters for resource utilization. For future space explorers, a cryovolcanic vent is a resource tap. It is a natural concentrator of volatiles for fuel, and, in the case of objects like 3I Atlas, potentially refined metals suspended in the gas flow. Comets are not dead. They are thermodynamic machines, ancient batteries slowly discharging the energy stored during the birth of the solar system. From the nitrogen geysers of the outer rim to the metallic breath of interstellar visitors, the phenomenon of cometary cryovolcanism reveals a universe where ice is as dynamic as fire. As our telescopes improve and our probes venture closer, we are learning that to understand the origins of our hot, living world, we must first understand the physics of these cold, exploding ones. Thanks for listening to G Fun Facts Online.